My talk is entitled Rapid On-Chip ELISA, aided by centrifugation-assisted thermal convection reflow. And although I am the opening talk for this session, I'll be tackling very little on optics and photonics, so apologies in advance. So moving on with this ambiguous title, I want you to focus on the thermal convection. So I guess pretty much everyone here is familiar with thermal convection, that when we boil water, a cyclic flow occurs due to the change in density. So warm liquid rise up and the cold liquid falls. So to be precise, we call this dynamics as Rayleigh-Bernard convection. And this dynamics is determined by buoyancy, and hence it's gravity dependent, and the inner friction that is related to the dimension of the container and thermal diffusion. So basically our idea is we come up with this design of confining the Rayleigh-Bernard convection flow in a ring microchannel and increase the gravity by virtue of centrifugal force. And we call this as centrifugation controlled convective flow, or simply C3 flow, where the idea is to control the flow speed by simply changing the centrifugal force. So by using this Boston's equation governing this dynamics, we can somehow find the relationship between the parameters that the temperature difference and the relative gravitational acceleration are the dominating factors. But the biggest question is how to realize this. So here, after several iterations of our design, we come up with this one. So where you have your hot source here, located here, and then you have your cold source located here, and the ring microchannel is how you see it in your screen. And the idea is to simply spin the microchannel together with the heaters. So we have published this back in 2017, and as you can see here, you have a cyclic flow that occurs, and the flow speed is solely dependent on the temperature difference and gravity. But in this case, we fix the temperature difference, and we just changed the g. And we did some basic simulation using COMSOL multiphysics to show that our result is coherent with the theory. So another interesting feature of C3 flow is enhanced mixing inside the microchannel. So the diagram here shows that along the microchannel, you have here your microchannel. So with a thermal convective flow, you have a secondary flow. And in this system, two forces can be responsible. You have your Dean force, which is generated on a curved channel, and the other one is your Coriolis force, which is generated in a rotating plane. So from our simulation on COMSOL multiphysics, secondary flow indeed happened in this system, but mostly it's affected by the Coriolis force. So the big question is, so what's with C3 flow? So what's with the flow controlled by centrifugation with enhanced mixing? So in our lab, we specialize in developing biosensing platforms. And one application of this flow control is micromixing in biochemical assay. So two of the most common diagnostic tools present in the world, applied in medicines and health, are the polymerase chain reaction, PCR, that detects the target nucleic acid and enzyme-linked immunosorbent assay, or ELISA, this one. Or some call it as immunosensor. And I guess most of us here have heard these terms because of the ongoing pandemic. And in this morning session, Dr. Cynthia Saloma mentioned the three methods for COVID detection, and you are already aware that it takes quite much time. And this long processing time is highly dependent or related to the long operation time due to the dependency on free convection. So by using the C3 flow, we can hopefully increase the rate of reaction and its efficiency. And aside from this, the system is a reflow type, meaning we can increase the chances of interaction of the target carrying liquid to the sensing surface. So this is very crucial if your sample is scarce or limited or in a small volume. So the real challenge in any biosensing platform is bringing your target to the sensing surface in addition to the detection performance. Another is that the operation will be much easier in this platform since you just simply change the rotation speed. by just a press of a button, for example. And most biochemical labs in any part of the world are very familiar with centrifugation. So adjusting to the new technology should not be an issue. And another thing is it's a closed system. It's a closed system, meaning you could guarantee minimal contamination. And most importantly, especially in the case of the Philippines, we could reduce the reagent consumption, which could significantly cut down the cost. So we have reported this system and the use of this system for PCR, but for today I'll be discussing its utility for ELISA. So this system composed of two parts, the two important parts. The first is the rotating heater stage and the microfluidic chip. So for the rotating heater stage, depicted here is the conduction scheme of the temperature sources. So what's important to note here is that the two heat sources have limited thermal contact because of the low conductivity of the polyether ether ketones. And the heating pads, with colored orange and blue, are in constant thermal contact with the sources, so while they are rotating. So you have here two conducting lines for each heat sources. The hot source here is controlled by a digital temperature controller, while the cold source here is connected to a night brine coolant. So depicted here on the lower left is the temperature profile, illustrating that the set temperature doesn't vary significantly for almost 20 minutes. Next is your microfluidic chip. It consists of layers of PDMS, or polydimethyl siloxane, which is biocompatible to most target and has high transmittant invisible light, which is very important for any optics-based detection. So the layers are adhered together by exposing them to oxygen plasma and in effect promoting a hydrophilic surface. So here is the assembly. So to fabricate these PDMS layers, we outsource a series of COP molds that are fabricated by mechanical drill. You have it here. And in the circular channel, we filled it with microbeads. 40% of its width is filled with 40% with polystyrene microbeads. Sorry for that. So these microbeads carry the capture antibodies and also promote further mixing. Also, if you will notice on the upper right, the channel design includes a U-shaped channel at the bottom of the circular channel with high depression to prevent the microbeads from escaping the circular channel. So putting together the rotating heater and microfluidic chip together, we presented here are the flow control and liquid exchange operation. So without the applied temperature, no circulating flow occurs. You only have your typical downward flow. So and you can see here that after some time, you can change the fluid. First it's red, and then afterwards it will be transparent by simply adding the liquid. So this automatically meters the volume of liquid that you put. So you don't have to worry about precise measurement. Afterwards, you turn on the temperature, and the temperature difference will promote the convective reflow. So right now the system is run at 300 G with a flow rate of 50 microliter per minute. So with this flow control, we can perform on-chip ELISA. So basically you put the solution with the target antigen into the channel, you allow it to interact with the microbeads, you wash the unbound antigens, then you add the solution containing the detection antibody. After interaction, you wash it again, and then add the chromogenic substrate, and then stop solution, and then lastly, you measure the absorbance. But what's important here is that everything is done in 30 minutes, from sample preparation to detection. So all of these experiments are done in a humidity-controlled environment, and the detection and measurement are done on a separate setup. So by measuring the value of the absorbance, you can determine the concentration of your target. So to test the device, we tried the quantitative measurement of human IgA, human immunoglobulin A, which is responsible for defense against respiratory infections, but it's non-selective. So with this device, you could monitor the concentration of IgA in your body and subsequently assess its condition. So I added here a simplified version of detection scheme for ELISA, or specifically it's sandwich ELISA. And as you could see here, we have a relatively good linear relationship of the calibration curve. But in any immunosensor, it's not the linear relationship that really matters, but the spike test, or how reliable is your calibration using another sample or media. And we could see here that uh, our system has high detection recovery of 98 to 105%, which is in the acceptable performance range according to standards. But this is still on a using a control solution. So we haven't tested it on actual samples, and we still need a larger sample volume. So in summary, we are able to reduce the operation time of performing ELISA from 2 to 3 hours in the conventional platform to 30 minutes using this C3 flow with reduced amount from 100 microliter to 24 microliter. And I can say that this is a great improvement, but hashtag disclaimer, this is still in the prototype stage and we still have a lot to improve in this system. So thank you very much, especially to my mentors and coworkers here in Osaka University and the funding from GSPS in supporting this work. And lastly, allow me to showcase our lab. My presentation today is all about microfluidics, but we are a biosensing lab and we have other technologies such as nano microprocessing technology and photonics technology that we use for localized surface class 1 resonance and screen printed electrode that are integrated to other platform. So we have a range of applications in the lab. So if you're interested in possible collaborations, please do email my boss, Professor Eiichi Tamiya, or my direct supervisor, Assistant Professor Masato Saito, or you could just directly send an email to me. So with that, that's it for me. Thank you very much for your attention, and I'll be glad to answer any questions that you might have.
Hello everyone, I am Dina Grace Bangilan from the National Institute of Physics, UP Diliman. And in this work, I, together with my advisor, Dr. Hermosa, tried to generate a new kind of vortex beam called perfect petal beam using a spatial light modulator. To understand more of this, we review the following terms. A petal beam is a superposition of two Laguerre-Gauss beams or two vortex beams with opposite topological charge TCM. The interference pattern is a circularly symmetric distribution that is modulated by a cosine function. A Laguerre-Gauss beam is one of the canonical examples of optical vortex modes. These are structured light fields with an azimuthal phase term of the form exponential im phi that carries an orbital angular momentum of mh bar per photon. Typically, these modes have a vanishing on-axis intensity surrounded by a ring of light whose radius increases with m. In specific applications, however, such as in particle trapping and manipulation, and in coupling multiple vortex into a fiber for communications, it is wanted to have a beam containing a high TC content and a small radius simultaneously. The key to this issue is the concept of perfect vortex beam introduced by Ostrovsky and colleagues in 2013. In this context, a perfect vortex beam has a fixed radius regardless of the topological charge encoded in it. In this study, we adapt the concept and known techniques to generate a new kind of perfect vortex beam called perfect petal beam. We employ one of the most convenient methods, which is based on holograms displayed onto a spatial light modulator, as this allows the generation of light with arbitrary phase and amplitude, including vortex beams and their superpositions. Inspired by the idea of vortex beams or perfect vortex beams and petal beams, we predict that we can also generate perfect petal beams, which will possess a property essential for the said applications. And to verify this, we realized two physical experiments. In the first experiment, we generate PPBs with varying M values, and in the second experiment, we generate PPBs with varying slit widths and varying radii R. Our experimental setup is shown schematically in Figure 1. A helium neon laser operating at 633 nanometers is properly polarized and collimated using a half-wave plate and a telescope composed of lenses L1 and L2. The collimated beam then impinges the surface of the SLM where the phase of the modulated light is registered. A third lens L3 is used to collect the diffracted light from the SLM and directed it onto an aperture that selected the first order diffraction spot. Lens L4 imaged and projected the spatial pattern onto the CCD. The phase in the SLM is a mass described by a circ function convolved to the phase of the superposed beams. We believe that by multiplying these two yields to a beam with invariant size regardless of the topological charge encoded in it. Our results from the first experiment are displayed in this slide. By inspection, the beams shown in figure 2 confirms that the size of the tip of typical petal beams increases with increasing magnitude of M. Moreover, we observe that the number of bright petal-like structures in the distribution is twice the amount of the topological charge encoded in it, given by the relation n is equal to 2m. Interestingly, the ring radius of the generated petal perfect petal beams remains constant for all orders of theses given that the initial waves of the beam at the SLM is constant. Apart from that, PPBs still exhibit 2m number of petal-like structures which are now thinner compared to the typical one. Further, except for m is equal to 3, the images exhibit a peculiarity. Artifacts evolved beside the primary lobes for large M, and we account this from the interference of each diffracted petal-like structure in the beam. Our results for the second experiment are shown in figure 4. The first three images from the left are generated using a circular function with varying radii r, while the last three images are produced using a circular function with varying slit widths delta r. Using slits of bigger r, we notice secondary lobes alongside each main lobe, and this may be accounted from the diffraction of light by the circular slit. And with wider slits, we allow higher transmission of light and hence we generate a more intense beam. Our these experimental results, we say that our fast generating technique produces a state of light with different features that can be used for different purposes. To examine the fringe distribution and to verify the presence of petal-like structures in the beams, we plot as shown in the left panel of figure 5 their intensity profiles. Here, we see a total of 8 peaks corresponding to m is equal to 4 and 40 peaks corresponding to m is equal to 20. This also confirms the presence of secondary peaks. Nonetheless, these peaks have no significant effect on the visibility of the fringes. The contrast, defined as the ratio between the spread and the sum of the minimum and maximum intensities, equals to 1, regardless of m. This means that we can distinguish precisely the intense primary lobes contained in the distribution from the secondary peaks and dark lobes. In summary, we have generated a new kind of perfect vortex beam called perfect petal beam using a phase-only spatial light modulator. We have observed that these share one of the well-known properties of a typical petal beam, that is, the number of petal-like structures in the distribution is twice the topological charge of the incident beam. It also has a vanishing core whose ring radius is invariant of the TC encoded in it, a property conflicting it with the typical petal beam, and a property it shares with the perfect vortex beam. Alongside the primary petal structures are secondary peaks which we believe are a consequence of peripheral interferences. Nonetheless, the contrast of the produced beams is equal to 1 regardless of m. This means that the artifacts or the secondary peaks are insignificant in defining the total number of peaks to be used in characterizing the beam. Finally, we thank these institutions for financially supporting our work. These are our references, and we thank you for listening.
Good day, everyone. My name is Mario Onglao, and today I have the pleasure of presenting our work on single plane diffuse illumination phase retrieval. My co-author for this work is Dr. Percival F. Almoro. So first, light is an electromagnetic wave that carries information. Being a wave, we can represent it using its amplitude and its phase. The amplitude denotes the highest value of our wave, while the phase tells us the location along the wave cycle. Both the amplitude and the phase can be used to carry information. For example, the amplitude can be used for conventional imaging or for spectral measurement. On the other hand, the phase can be used to measure index of refraction and for phase contrast imaging. One advantage of the amplitude is that it can be easily directly measured using conventional sensors. However, the phase often requires indirect methods in order to retrieve it. One example of an indirect method is the multiple plane phase retrieval, or MPPR. MPPR, from the name, uses two or more images captured at different axial camera planes. So here on the slide is an example of a recording setup. An expanded laser illuminates an object, and the scattered wave is captured by a camera. At this camera plane, we take an image and we call that I1. We then translate the camera a distance dz and take another image, calling it I2. So we repeat this process each time moving the camera a distance dz and taking an image until we get n intensity measurements. These intensity measurements will then be processed by an iterative algorithm in order to retrieve the phase. For cases when the object is smooth, such as a lens, we can introduce a diffuser in order to enhance the spatial variation. So throughout the years, there have been some modifications to MPPR. In 2012, Agur et al. Proposed the fixed camera MPPR. The expanded laser beam passes through a glass diffuser, which then illuminates the object. The scattered wave is captured by a 4F lens setup with an SLM in the Fourier domain. On the SLM, we project different transfer functions, which can virtually propagate the object wave. This means we can fix the camera while still virtually recording at different camera planes. Next, in 2016, Almora et al. Proposed the SLM-based diffuse illumination MPPR. For this technique, they retained the translated camera, but they replaced the glass diffuser using an SLM as a diffuser. This has the advantage of being easy to tune and flexible. So depending on the specifications of your setup, you can easily change your diffuser. The goal of this work is to combine the two techniques into one. So here's the setup. An expanded laser beam passes through an object, and the scattered wave is captured by a 4F lens setup. On the Fourier domain, we place an SLM with a combined diffuser and transfer function. Using this technique, we get the advantage of a tunable SLM diffuser as well as a fixed recording plane. So with that, what do we actually project onto the SLM? So we project a modified transfer function denoted by TDiff, which is equal to the transfer function of free space times a modification function U mod. To get U mod, we need to generate a guess object U naught and a phase diffuser D. To get U mod, we get the Fourier transform of U naught times D divided by the Fourier transform of U naught. So with that, here are the objectives of the study. We want to reconstruct simulated wavefronts using the proposed technique, and then compare reconstructions to other MPPR techniques. And lastly, we want to test the dependence of the technique on the guess object U naught. Here are the reconstructions for various techniques. So for these results and the succeeding ones, our target is a spherical lens with a circular aperture. So the intensity is a flat circle, and the phase is a spherical function. Here are the reconstructions. For conventional MPPR without a diffuser, we are unable to reconstruct the intensity and the phase. For diffuse illumination, or the 2016 version, and the proposed technique, we are able to reconstruct both the intensity and the phase. Next, we want to check the effect of the phase depth of the diffuser D on the reconstructions. So the results on this slide is actually additional data that cannot be found in the manuscript. We are checking the reconstruction for two techniques, the 2016 diffuse illumination version and the proposed technique. So when the phase depth is 0, meaning we have no diffuser, we are unable to reconstruct the phase. For appropriate phase depth, we are able to reconstruct the phase. And for some values of the phase depth, we're only able to reconstruct the phase for one technique. So for this example, we were able to reconstruct for diffuse illumination, but the algorithm failed for the proposed technique. When the phase depth is much higher, both techniques fail to reconstruct the phase. These results show that the two techniques have a different range of functional phase depth in which they work. And last but not the least, we want to check the effect of the guess object on the reconstructions. So on the first column, 1A and 1C, we show the guess object when it matches the target. And for the second column, 1B and 1D, the guess object does not match the target. So when the guess intensity and guess phase are both correct or they both match with the target, we are able to reconstruct the intensity and the phase. When the guess intensity is wrong, but the guess phase is correct, we are able to reconstruct the phase and we have some noise in the intensity. When the guess phase is wrong, we get very low contrast reconstructions. And last but not least, when both guess phase and guess intensity are wrong, interestingly, we were still able to reconstruct the phase and there's still some noise in the intensity. These results show that the phase is retrievable even if the guess object is different or mismatched from the target. So to conclude, a novel technique that uses a combined transfer function and diffuser function projected onto an SLM in the Fourier domain is demonstrated in wavefront reconstruction. The technique performs similarly to diffuse illumination MPPR, but with a different range for phase depth. Initial results showed that the technique can still retrieve the phase even for a mismatched guess object. And lastly, looking forward, the next goal of our study is to remove the dependence on the guess object. That's all for now. Thank you all for your attention. If you have any questions, feel free to email us at this address, or you may access the full manuscript using this QR code. Thank you.
Yes, we can hear.
All right, thank you. So, good day. My name is Renish C. Simon. On behalf of Dr. Nathaniel Hermosa, I'll be presenting our work on a model that describes the optical response of a 2D material. So, I'd like to start with showing you the Fresnel formulae. This is perhaps one of the most famous sets of equations in optics. The Fresnel coefficients describe the field amplitudes of the scattered wave at the interfacial boundary of two media. Equations shown here are derived by matching the tangential fields of the electromagnetic wave in the incident and transmission regions. The fields are usually assumed continuous since there's no charge or current distribution formed within the interface. However, the physical realization of 2D materials makes us reconsider these boundary conditions. A flat 2D material can be a source of a surface current at the interfacial boundary according to the studies of Zhang et al. And Merano. So we synthesize these previous works and come up with a response function for these sources of surface current. And we also constructed a transfer matrix for the corresponding electrodynamics. So a monolayer of 2D materials such as graphene and hexagonal boron nitride is just an atom peak. So this is why some researchers would model it as an infinitesimally thin sheet which we call as the perfect sheet. So we propose an optical response function for a perfect sheet material. The response function is derived from the conduction and polarization current generated within the perfect sheet as a reaction to an incident field. And if we assume harmonic time dependence, we arrive with the response function epsilon equals to sigma minus I omega epsilon naught chi. Here, sigma is the conductivity of the perfect sheet, while chi is the two-dimensional equivalent of the electric susceptibility. Omega is the angular frequency of the incident light. So the response of the material with the field is summarized by the equation Js equals epsilon E. Then we derive a transmission matrix that considers the response function of the perfect sheet. Suppose we have a system composed of two semi-infinite media, L and M, and at the interface, there is a perfect sheet. Consider the p-polarized case where the incident wave is described by the magnetic field wave function as shown, and the corresponding electric field counterpart is can be derived using the equation shown. Applying the boundary conditions for the tangential fields, we can write a system of two equations, which can be compactly written in a matrix equation. So following the same fashion, we can derive another matrix equation for the case of the S-polarized field. And it is easy to show that the matrix T, which is the transmission matrix, is given by this expression. It is a 2x2 matrix with an element has three terms. So for the cases that there are thin films in the optical system, the wave propagation within the thin film is taken care of by a propagation matrix P. So the effective transfer matrix for a stratified media is a matrix product of the transmission and propagation matrices. So we can assign a transmission matrix at every boundary of a transmission matrix at every boundary and a propagation matrix at every thin film. Using a standard scattering matrix approach, we can derive expressions for the reflection and transmission coefficient in terms of the elements of the effective transfer matrix. And with this results, we investigate the effects of the perfect sheet in terms of absorption, reflection, and transmission of light. So we examine the effects of the response function epsilon by considering the time averaged version of the pointing theorem. And then we compare it to the results when the absorptivity is calculated using the transfer matrix approach. And here we show that the imaginary part of the response function has a little effect on absorption, as we can see in the absorptivity plot. We have calculated that the absorptivity using this alternative, and we compared it with the results in the literature. The absorptivity of 2.3% is calculated for a freestanding graphene at normal incidence. We also observed that the graphene absorbs S-polarized light better at glancing angles, and then it rapidly dies down at incident angle as the incident angle approaches the perfect glancing. So the perfect sheet model tells us also that the electric susceptibility of graphene affects the reflectivity only by a small amount. We also investigate a non-conducting 2D material. So the boron nitride is invisible, but if you incorporate a thin film, it will improve its visibility. So if you want to more about perfect sheets, we have a poster presentation in day 3 entitled Improve Visibility of Boron Nitride on Oxidized Substrates at Pseudo-Booster Incidence. So here are my references. We would like to express our gratitude to DOST Preserve for funding assistance, and I'd like to thank NSky Corporation for providing me a place to conduct this presentation. You may scan this QR code for more details. Thank you.
Good afternoon, everyone. My name is Anthony Fox, and I'll be presenting our paper entitled The Axial Response in Semiconductor Laser Confocal Interferometric Microscope Under Full Optical Feedback. My advisor and co-author is Dr. Cesar A. Saloma, and we are from the National Institute of Physics in the University of the Philippines. Okay, so in our paper, we compare 3 interferometric configurations under optical feedback. We compare it in terms of the axial response and the contrast. So we found that the full feedback OSMI configuration gives the highest contrast among the 3 that we have shown, and the narrowest axial response, which is actually beneficial for confocal microscopy. Okay, so the optical feedback semiconductor laser Michelson interferometer, or the OSMI, can measure the full displacement of a reflecting sample, as shown here, mirror 2. But this differs from a single channel configurations because there are 2 external cavities. So the full displacement is measured from the asymmetry produced by the OSMI, as shown here, and it changes due to the optical path difference between mirrors 1 and 2. So in order to calculate this, we would first need to reduce the OSMI into an effective Fabry-Pérot cavity, where these terms are the external cavity terms, or all the path taken by the output beam. Okay, from here we can get the effective reflectivity of the external cavity, and from work done previously, the perturbation power is proportional to the natural logarithm of the front facet and the effective external reflectivity. So we compare the OSMI with the optical feedback Mach-Zehnder interferometer and the full feedback OSMI, as shown here, in terms of the contrast in interferogram and the actual response under confocal configuration. So here, in all numerical calculations, the wavelength of 832 nanometers is used, and the distance between all optical components, as shown here, is an integer multiple of the wavelength, so 8.32 centimeters. Okay. So in order to get the interferogram of a Mach-Zehnder interferometer, is much simpler than the full feedback OSMI. We would, again, need to get the external cavity terms that are connected with all of the paths taken by the output beam here. So there's a total of 6 paths, and the perturbation power is, again, proportional to the natural logarithm of the front facet reflectivity and the effective reflectivity of the external cavity. This differs from a traditional Mach-Zehnder interferometer because, 1, there are mirrors in the classical viewing area, and 2, X and W are beam splitters, and Y and Z are the mirrors. So this configuration of the Mach-Zehnder interferometer is for displacements in the MZ interferometric arm, which wherein you don't need refractive materials, okay, in order to induce imbalance in that arm. Okay, so this is the interferogram map with respect to the sample mirror displacement, mirror 2, and the additional OMZI balance. The imbalance periodicity is lambda. As you can see that peaks, the highest peaks are at lambda periodicity, and the interferogram periodicity is the same as the OSMI, lambda over 2. It is important to note that a slight imbalance causes a dip in the peak intensity of the interferogram. Okay, so for the full feedback OSMI, again, we would need to consider the optical paths taken by the output beam, which in this case is infinite because of mirror 3 reflecting onto mirrors 1 and mirrors 2. Okay, then back to the front facet. So because of this, we have developed an iterative process where we calculate first the propagation jump number. So for example, for a propagation jump length of 2, the beam goes to A, B, and A, and A, C, and A, which is the OSMI effective returning beam. And hence we can get the effective reflectivity of the OSMI. Okay, so as we increase the propagation jump length, we compare that interferogram with the previous one, and we calculate the root mean square deviation. And the process stops when the RMSD is less than 3%. So for example, there are about 1 million external cavity terms at propagation jump equal to 38. And this is the output interferogram. Okay. So we compare the interferogram of the OSMI, the OMZI, and the full feedback OSMI in terms of the contrast and this displacement sensitivity. So the contrast here, clearly, the full feedback OSMI has a higher contrast than the OSMI and the OMZI. And the slope of the full feedback OSMI from the maximum value to the minimum value is larger than the OMZI and the OSMI. Now, in order to compare it into a confocal configuration, we would need to consider the effect of an objective lens or the axial response. So for NA, the NA to be used is a 0.5, 0.85, and 1.4, okay, as shown here. So after calculating the axial response of the different numerical apertures, we get this traces. From here, this actually modulates the effective sample reflectivity of the mirror or a sample. So under a confocal configuration, the interferogram is shown in figure 11A from -4 to 4 micrometers. You can see that for NA 0.5, clearly it follows the envelope of the axial response of the objective lens. So for lower NA, more interferogram peaks are present, as shown here. Okay, so as we zoom in from negative lambda over 2 to lambda over 2 sample mirror displacement, we see a confocal axial response of the OSMI, OMZI, and FF OSMI, wherein at a higher NA, at most the full feedback OSMI peak decreases at 52%. At here 0 and negative lambda over 2. Okay. All right. So other than that, the full width at half max of each of the configurations are shown here, wherein the full feedback OSMI has a much smaller value for the full width at half max. This means that it has a higher resolving power and it's more sensitive to the axial response of the sample mirror, which is perfect for imaging and confocal microscopy. So our conclusion is that we get the theoretical solution for the optical feedback Mach-Zehnder interferometer and full feedback OSMI. The full feedback OSMI contrast at 2.16, displacement and reflectivity, this sensitivity is better than that of the OMZI and the OSMI. For the confocal axial response, we see that the axial response of the imaging lens, the objective lens, modulates the effective sample reflectivity. So at lower numerical aperture values, more high power interferogram peaks are present. At high numerical aperture values, at most 52% decrease in neighboring peaks for the full feedback OSMI. And the full feedback OSMI has a sharper axial response than the OMZI and the OSMI. So that's my presentation. Thank you.
Good day, everyone. This is Jonel F. Binamira from the National Institute of Physics, and we are going to present our study about enhanced reconstruction of axially extended objects using phase retrieval with unordered propagations and compressive sensing. Our study is about phase retrieval, a family of non-interferometric techniques that recovers the wave field, including the amplitude and phase of an object using at least two intensity images. There are many techniques that fall under phase retrieval. One of them is the single beam multiple intensity reconstruction, or SBMIR. Here, we have intensity images of the object and a numerical error-reducing algorithm to get its phase. From here, we can get information about the object, such as deformations, refractive index, and more. Here's the typical setup for SBMIR. We have a camera placed at distance d from the object, which is illuminated by a laser beam. After taking the image of the object there, the camera is moved at distance delta z from its previous position and takes the image of the object there. The process is repeated until you get the desired number of intensity images. This setup is advantageous because it is simple and non-interferometry. It is also not prone to mechanical vibrations. Next is the use of an iterative algorithm using the recorded intensity images. One iteration of the algorithm involves wave propagations that proceeds sequentially from the first intensity image, I sub 1, to the last intensity image, and back to I sub 1. After that, the wave field at I sub 1 is propagated back to the object plane. However, one disadvantage of this algorithm is that it is prone to phase stagnations, like what is shown here. It occurs when intensity images have low intensity variations. One method to solve this problem is to perform the iterative algorithm such that wave propagations proceed in an ordered manner instead of sequential. We call this algorithm USBMIR. For wave propagations, SBMIR uses the Rayleigh-Sommerfeld diffraction equation, or RS. Here's the digitized form of RS equation, which relates the field at the output plane and the field at the input plane via this transfer function, which is related to the illumination wavelength lambda and propagation distance z. In the iterative algorithm for SBMIR, the field at one plane is propagated to the next plane using RS equation. Next, the amplitude of the estimated wave field is replaced by the measured intensity image at that plane, while the phase is retained to get the updated wave field. For the next propagation, the updated wave field will serve as the input wave field, and the process is repeated all over again. One problem for SBMIR is that it is difficult to implement for axially extended objects like this. For such objects, reconstructions at the object plane may have diffraction artifacts from adjacent sections, especially if occluded elements are present. One solution for this is to incorporate compressive sensing in the reconstruction process. Compressive sensing are methods that takes account the property of the signal. In this study, we will use the total variation or TB minimization approach in compressive sensing, and we will apply it to the back propagation to the object plane. It is done by solving this equation, where this term ensures that the estimated wavefront is close to the RS propagated solution. This term, the total variation, smoothens out the noise, which have typically lower TB values compared to the edges. This parameter, tau, is the regularizer, which balances the two terms in this equation. In this study, we performed the simulation for two sets of actually extended objects. Test object 1 has two sections, U and P. Test object 2 has an USAF resolution chart occluded by a Shetland phantom object. For both test objects, the sections are separated 2 centimeters apart. Here are the reconstruction parameters. We recorded 15 intensity images for each test object, and we performed 20 iterations of USB mirror. After that, we backpropagated the resulting field to the object planes using two methods. One is by direct RS backpropagation, and the other one is by applying compressive sensing. Here are the reconstructions at different sections of Object 1. The top row shows the reconstructions using conventional backpropagation, and the bottom row shows the reconstructions with compressive sensing. This corresponds to this section where P is reconstructed, while this corresponds to this section where U is reconstructed. Notice that with compressive sensing, diffraction artifacts are minimized. This is because the TB term in the compressive sensing framework minimizes the noises, which typically have lower total variation or TB values, while preserving the edges of the object. On the other hand, here are the reconstructions for test object 2, where USAF resolution chart is occluded by the phantom object. But let's look at this section in detail. If you zoom in at the center, you will see that with compressive sensing, reconstructions of occluded elements are clearer compared to the reconstruction with direct backpropagation. Also, notice that diffraction artifacts are minimized for reconstruction with compressive sensing. To end this report, here are the summary and conclusions. From the qualitative results, phase retrieval with unordered propagations and compressive sensing successfully reconstructed sections of axially extended objects. We can apply this algorithm to the non-destructive analysis of two-dimensional sections of objects. An outlook for this is to investigate objects with phase type occluding elements. That's all. Thank you very much.